This is the lecture on section 6.5, average value of a function. And the point of this section is to use the following formula for the average value of a function on an interval a, b. So the formula is that the average value of the function on this interval is 1 over the length of the interval times the integral from a to b of f of x dx. And if you think about this as in terms of areas, adding up the small areas of rectangles and then dividing by the total width of the bases of the rectangles, this makes sense. You can see a derivation for this formula at the beginning of this section, starting on page 451. For example, if we look at the function g of t equals t over square root of 3 plus t squared, then the average value on the interval from 1 to 3 is, we would call that g sub av. That is 1 over the length of the interval, integral from 1 to 3 of that function dt. And to evaluate this integral, we would use a u substitution. U equals 3 plus t squared, du equals 2t dt. Changing the limits of integration, we would find that this is, so have the fraction 1/2 out front, and then in order to make the substitution, I would multiply by another copy of 1/2, integral from 4 to 12 of u to the 1/2 du. And evaluating this integral, we would end up with square root of 3 minus 1. I'll leave it to you to fill in the details for the computation of that integral. Now, as an application of this, we have the mean value theorem for integrals. So, mean value theorem for integrals. And this will look very similar to the mean value theorem that we saw in Calc 1, Math 1060, except that it uses the average value of the function. So if I have a function f of x that's continuous on the interval from a to b, then there is a value c inside that integral where the function achieves the average value. In other words, the value of the function at c is equal to 1 over b minus a times the integral from a to b of f of x dx. So for example, with our previous function, g of t is t over the square root of 3 plus t squared on the interval 1, 3. This is a continuous function. The denominator, so 3 plus t squared is always positive, so the square root is always positive. I have a quotient of continuous function, so it's continuous. And so we can find the value for c inside the interval from 1 to 3 such that f of c equals that average value. And so what that means is that we're going to take the function, sorry, those should be g's, since my function is called g in this example. And so what I do is I take my function g, and I set it equal to the average value that we found on the previous page, which is square root of 3 minus 1. And we solve for t. And I won't do all the steps for this. The first step is to square both sides. T squared over 3 plus t squared equals square root of 3 minus 1 squared, which is the same thing as, when you work it out, 2 minus the square root of 3. Sorry, that should be 4 minus 2 square root of 3. Not sure why it won't let me erase that. And when we solve that by cross-multiplying, we end up with t equals plus or minus the square root of 6 times 2 minus square root of 3 over 2 square root of 3 minus 3. And then we only worry about the positive square root because we're in the interval from 1 to 3. And the value we get is approximately 1.8612. This has physical applications as the regular mean value theorem did and the regular function values. So for instance, we'll consider an example from Calc 1, which was the exponential growth section, page 238, example number 1, modeled the world population in the second half of the 20th century. So that model is an exponential model, and we found it to be P of t is 2,560 times e to the following exponent, 0.017185 t. And here t equals 0 is the year 1950, and t is measured in years. And with that model, we find that the average population in that time interval we would write that as P sub av, and that is 1 over the length of the time interval times the integral over the time interval. And that's from 0 to 50, because t equals 0 is 1950, then t equals 50 is 2000, and then we integrate the model function. And that's a straightforward integral to compute. I'll leave that to you. This is the end of the lecture on section 6.5.